So without further ado, please help me welcome Rob Levy to introduce Lorraine Remer.
Hello. I don't know if I need a microphone, but I guess I've been at Goddard. I've been at Goddard for 14 years now, and a real reason that I came here is because I met Lorraine right on and decided that this is the place I need to come. With being in the group of just wonderful people with Lorraine, and of course Yoram Kaufman and Shauna, who've been here for a long time, and it's a great group. And I don't know, everything. I don't have it memorized, all the details about Lorraine's previous life, but I know she's been at Goddard since 1991. Is that right? I think so. And then she officially became a civil servant just before I became a contractor here in 1998. And she's been doing just amazing things. And now, most recently, she left early last year and has now been at UMBC for the last year. Again, doing just great stuff when it comes to aerosol research and branching out and doing all kinds of other things too, including recently starting her own company and making some just crucial equipment and tools that all of us doing aerosol research are just dying to get our hands on and to have measurements all over the world. Oh yes, money, she's saying, but show me the money. But anyways, for the last, I guess, 14, 15 years, it's been amazing working with Lorraine, and she really knows how to make it fun, not just for girls, but even for some boys. We all have fun here. So, I guess without further ado.
I have multiple wires here. I got so many wires I could join the FBI. Okay, and there's all kinds of cool things. First of all, they gave me 2 pointers of different colors. So anyway, thank you very much for inviting me. This is kind of a strange talk to come and give, because you're supposed to come and talk about what you're doing and how you got there, and gosh, and I just don't feel old enough to do this. Something I don't mind doing on my retirement, but this was kind of strange because I feel like I'm almost like halfway. I'm halfway through, not near the end. Anyway, girls just want to have fun, and I pose this question because everyone asked me why I left Goddard. No one asked me why I came, but let's tell the story, and maybe we'll have some answers by the time we get to the end. And I did start July 16th, 1991. I arrived at Goddard on a postdoc, and I came because of 2 men. One was Yoram Kaufman, who was not yet a civil servant. He was working for USRA at the University of Maryland, and Om Pahiti, who was the president of SSAI. And this story is really interesting. In 1988, and if you can see this is the 1991 line when I came, so we're going to be looking in both directions, back and forth. So if you need your bearings, you can always look at the top of the page. This is a proposal that Yoram Kaufman submitted to NASA to be a MODIS team member, and he's proposing the global monitoring of aerosol properties, climatology, atmospheric corrections, biomass burning, and the effect on clouds and radiation. This is what he proposed to NASA, and if you notice, he proposed it from SSAI, and his signature and Om's signature. So the original MODIS proposal was submitted by SSAI. Why does Yoram submitting through a company when he's part of USRA and the University of Maryland? Interesting story. He wrote the proposal. He started its routing procedure through the University of Maryland. It got to his department chair. His department chair called him in and said, Yoram, we're not supporting your proposal. We have 2 other proposals for MODIS team member, and we want them to win, and we don't think you have a chance, and we're not supporting it. We don't think that the university could get 3 proposals funded under this call. So Yoram he was like 2 days before the deadline, and he had to find something to do. So he called up Om, and there's a long history with Om. And he said, would SSAI submit this proposal for me? And OM said, of course we would. So what happens? Yoram wins. The other two don't. Good guys always win, right? And because of that, because this was an SSAI proposal, when they did win in 1991, SSAI, and I have these originals at home, and this is all smudged because it is smudged. I have these originals, and I just scanned them for this talk. SSAI could submit an uncompeted proposal because they had already won the competition, right? So they came in as support of MODIS team member Yoram Kaufman. So they didn't have any competition, and they had a 10-year grant through this MODIS team member thing, okay? And if you look in the SSAI's proposal, in Section 6, the management plan, it says, in 1991, we expect to hire one permanent key person. And that was me. Okay? Wow. So that's the story of how we all got to get connected here. So I came in 1991. But let's look at Yoram's proposal before we go on, his science objectives. Developing methods, remote sensing of optical thickness, single scattering albedo, and particle size. He intended to do single scattering albedo for MODIS. Produce routine information on the global characteristics, develop methods for atmospheric correction, study the effect of aerosol on the environment, including cloud albedo, and use aerosol as a tracer to study biomass burning and anthropogenic emissions. So it was a very comprehensive proposal. This was not just to produce a product, this was to produce science. And that's the way Yoram always looked at things. Okay, so I wanted to stop and look a little bit about aerosol remote sensing at this time in 1991. What did I walk into when I walked into Goddard? And we started, this is aerosols, because I noticed there's a lot of people in the audience who are new. And I always had thought that if I start talking about what is an aerosol, people would laugh at me. But aerosols are the particles that are suspended in the atmosphere, and they can be liquid or solid. This is pollution particles from Los Angeles, but you can get smoke, you can get dust, you can get sea salt, you can get all kinds of different kinds of things. And by measuring the reflected radiation from the sun at the satellite, you can infer information about those particles, because as sunlight interacts with the particle, it scatters in a variety of angles, it scatters in different wavelengths. Some of the light is absorbed and depends on the color. And there are all these different pieces of information that you can get from remote sensing. The equation that governs the kind of remote sensing that we do looks like this. That the radiance measured at the satellite for a particular geometry, these are angles, and loading, and that's the total optical thickness that includes the gases in it, is equal to the radiance that comes from the atmosphere itself and the radiance from the surface. This is the surface reflectance, R. This is the radiance at top of atmosphere and the transmission through the atmosphere. So that the techniques that had been applied to this equation before 1991 were mostly dark target algorithms. And these came from, if you worked with scenes where the R was small, where the surface reflectance was small, and for example, over the ocean, as you get to slightly longer wavelengths, the surface reflectance goes almost to zero. It's very, very dark. So you could ignore that term. It simplified your problem. And you could model the type of aerosol that you were looking at, kind of guess what it is, guess what its properties were, and back out the optical thickness from what was measured from satellite. And this started with the MSS on ERTS, which became Landsat, the Landsat series. Griggs 1975 is the first reference I can find who applied this over water. Bob Fraser, 1976. Yuri Meckler, 1977. Yuri Meckler is Yoram's advisor, PhD advisor from Tel Aviv University. Bob Fraser was here in the climate and radiation branch, and he was Yoram's mentor when Yoram came here. So this is kind of that background. There's also work by Howard Gordon early on that focused on the atmospheric correction. And I'll explain to what that is in a little bit too. So then by 1988, Jorm tried it over land. Now, there was like this, you could do it over ocean, but what could you do over land? And he kept working with the dark target algorithm, and what he ended up doing was that he took a scene, a Landsat TM image over Washington, D.C. on a very hazy day, and he plotted that radiance against the radiance pixel by pixel on a clear day, close in time. And he got these clouded points. So if you look down here at a dark target, the difference between the clear day and the hazy day is this elevation. As the aerosol went over the dark target would brighten, and the satellite would measure more radiance than if the aerosol wasn't there. And you can use that information to back out information on the optical thickness. Okay, and this is the heart of all the dark target algorithms. And if you looked at the histograms of the AOT derived this way at the two different wavelengths that Jorm did, the clear day and the hazy day, you can see there was a vast separation. This hazy day was hazy. I mean, it was optical thickness of 1 and 1.25. So it was a very hazy day over Washington. And the little arrows down here that you barely see are the Sem Photometry measurements for validation. So especially in the 0.65 wavelengths, he got pretty good validation. The other interesting thing to look at over here in this plot is that at some point it crosses the line, and the hazy day equals the clear day. And if you go beyond that, the hazy day is actually making the scene darker, not brighter. And that's because the aerosol is absorbing some of the sunlight, and a very bright surface is going to look darker. So this crossing point is called critical reflectance, and that's where Jorm was going to get the single scattering albedo from. That is the measure of the aerosol absorption. Okay? So this was in 1988, just as he was writing that MODIS proposal. This is what he was thinking when he made the proposal. Clean days, hazy days, okay? We also had AVHRR back before 1991. Now the problem with AVHRR was that it wasn't calibrated very well. And I took this from something that Eric Remote did. And you can see how the calibration for each different AVHR sensor as a function of time after launch, how it degrades. So in order to do an aerosol retrieval from an AVHR satellite, first you had to calibrate it. And you had to calibrate it by means of like vicarious calibration, by looking at targets on the Earth's surface and doing the calibration that way. And it was a lot of work, and we did it occasionally, but it was not fun. But MODIS is going to have on-board calibration sensors. I mean, this was enough to do cartwheels over, okay? So it was a major improvement, just the technology. So while the satellite era was introducing aerosol remote sensing based on reflected light, there was a much older remote sensing method using Sem Photometry. And now this involved the sunlight and the extinction of the sunlight through the aerosol layer into an instrument here. So there would be the sunlight at the top of the atmosphere, and there would be the sunlight, the irradiance that was measured at the instrument itself, and it would be an equation like this. And you could do this to make very accurate measurements of the aerosol loading from the surface of the Earth. This is an ancient method. It started with Langley in the 1800s. And this group, this is the Smithsonian group, it's very famous. Their interest was not the junk in the atmosphere, which is our interest. Their interest was actually trying to measure the solar irradiance at the top of the atmosphere. You were trying to estimate what that was. So if you measure the sunlight at the surface at midday, you have a very small path length through the atmosphere. But as the sun, earlier in the day or later in the day, the path length is longer and longer, and the horizon is very long. So this is the secant of the solar zenith angle. It's 1 over the cosine of the solar zenith angle. And early in the morning, it would be out here, and then you would approach 1 as you got towards noon. And if you extrapolated, you could get what it was at 0, what the path length would be at 0. It's very clever. And that's why you would get the solar irradiance when the path was 0. When the path was 0, that would be at the top of the atmosphere. Okay? But you could also use something like this to estimate what's in the atmosphere and the extinction through it, which is what the Sem Photometry is all about. There was some interesting Sem Photometry in the 1960s by Flowers mostly and by Volz in Europe. And they were using, they were measuring something called turbidity, which is this beta in this equation. This is the angstrom exponent, and this is the turbidity. And this is from Flowers' paper in 1969. He had handheld Sem photometers all around the United States. And each plot is the seasonal distribution from January to July to December. So you get the annual cycle here. He could plot up and contour it by hand. Wasn't it nice back in the 60s? And you get the turbidity across the United States. This kind of interest sort of disappeared after the 60s. And because during the 80s, Sem photometry was mostly in support of something called atmospheric correction from satellites. People had satellites. They were interested in getting the surface reflectance. And the atmosphere just got in their way. They didn't care about it. They didn't want to quantify the aerosol extinction. It just got in their way. Get rid of it. Let me measure the surface reflectance. That was atmospheric correction. So this, for example, is one of the papers. This is Brent Holben's paper. Temporal and spatial variability of aerosol optical depth in the Sahel region. Already that sounds exciting, how the aerosol changes. In relation to vegetation remote sensing. Now, if he didn't have that phrase here, he probably wouldn't have gotten funded to do this work, because all the funding was in support of satellite atmospheric correction. They went out into the Sahel with handheld Sem photometers, and it was horrible conditions. Tom Eck still talks about it. And it made them think that there's got to be a better way. So this is a predecessor to a better way. So the situation that I walked into in 1991, Sem photometry was ancient, but the money of Sem photometry was all tied to atmospheric correction. Satellite remote sensing of aerosol, except for the occultation measurements in the stratosphere, was also tied to atmospheric correction. Satellite remote sensing was all dark target. Landsat was expensive. You had to buy each individual Landsat picture image, and you couldn't do anything global from it. AVHR was barely calibrated, and Goddard, with these people, was the center of the action in 1991 of all this stuff. And then there were stirrings of aerosol and climate, and it wasn't everybody was thinking about it. These are some major papers at the time. So people were thinking about aerosols and climate, but it was not like there in 1991. So if we look back at Yoram's proposal, the stuff in blue was really very innovative to get a global picture, to study the effect on the environment, and to extend it to biomass burning, because everybody was talking about anthropogenic emissions. No one looked at the biomass burning, and it was huge, okay? So this was the major things. Now, so this is 1991. I didn't walk in here completely, I had history too, so that was the history that I walked into. But now, I was 32 years old at the time, and I was married. I had 2 kids, and they were 5 and 2. And I had the first draft of my PhD dissertation on my advisor's desk when we left Davis. And we drove 2 weeks and came out to Baltimore, camping along the way with a 2-year-old and a grouchy husband. This is the house I grew up in. I had a growing up of the kind of lifestyle that you're trying to all give your children. Both my parents were college educated. My mother was a homemaker. She had a bachelor's degree from Berkeley, double major in anthropology and English. She had her diploma above the kitchen sink in the kitchen. She's very happy. She didn't want to do anything else. My dad was a physics major from UCLA who went to law school, and he was a deputy district attorney in Los Angeles County. I grew up in this house in Sherman Oaks. I did a lot of things. I had all those opportunities that you're trying to give your children. The one that really clicked with me was Girl Scouting. I'm still a Girl Scout. This is my classmates and my ship. We were Mariner Girl Scouts. Mariner Girl Scouts are a special type of Girl Scout that's no longer active. We learned mariner skills. I learned to sail, canoe, row, learned the knots, learned the first aid, learned a lot of useless information, like what's a sloop, a schooner, a ketch, and a yawl. I know that stuff. But we also learned a lot of things. One of my favorite topics was weather, tides, and currents. And we went and we competed on these skills. And this is my specialty. I could tell you about what the rise of the tide was, what the fathoms on the charts were, what I could read a barometer, I could do a sling cyclometer. I mean, I was really into this. And I would say this is the start of...
A weather weenie?
No, it was a little, not quite the weather weenie. You were different. I was a mariner. Okay. And this is probably my start of where I became interested in atmospheric science. Okay. And this is Sherman Oaks. This is my house. This is the park we played in. That's my elementary school would be up here, the junior high, my high school. My library is over here someplace. And if you get a bit better perspective, there's my house. This is the valley. I was a valley girl. This is the beach that I learned to surf on. Anybody else here surf? You know, the difference between a natural and a goofy foot, you know? So, and I went to UCLA for a year concurrent with my senior year in high school because my high school didn't offer calculus. This was before you had calculus in high school. And then I graduated in 1976, and I started school at the University of California, San Diego. I was 17 years old and an undeclared major in search of a Renaissance education. I wanted to learn everything. I wanted to learn history and humanities and literature and science and math. And the school down there really was like that. It was really excellent. But if I had stayed, I would have graduated a degree in mechanical engineering. And I didn't want to be an engineer. I mean, it was easy, but I didn't want to. So I left and I went to UC Davis. Now we go up the state to UC Davis is up here. And I became a junior transfer in atmospheric sciences. This is 6 of us. We were a class of 14, very close-knit group of kids. And we were studying weather. And in 1980, I graduated Davis, a degree in atmospheric science, and now we go back down the state to San Diego. And I started at the Scripps Institution of Oceanography for the tides and currents part of weather, tides, and currents. So I have a degree in physical oceanography also. I brought something down with me from Davis. This is Richard Kleidman, and this is us at the Scripps Snack Bar sometime in 1980, 1981. And he stuck with me. Richard Somerville was my advisor. I was in a PhD program. I got A's in my classes, but I couldn't pass the oral exams. And I left with a master's in 1983. My master's thesis grew into this paper, Somerville and Remer, 1984, which at the time was a very splashy paper, got a lot of publicity. It has a lot of citations. But what was next? Well, I was going to give a very feminist talk, but I decided not to. I couldn't hold back. These are things I heard at Scripps. Women are okay at theoretical work, but they can't do experimental work. Kathy, who was an older graduate student, about 5 years, she was married, she was pregnant as she was finishing her dissertation. Kathy shouldn't be having a baby, it's a bad career move. That got me more angry than probably anything, because the man who said it had 2 kids. And I'm not taking women on this cruise. There's nothing to discuss. Now, this was told to me by the professor who was the chair of the qualification committee that kept failing me. Okay? And I'm not saying that he failed me because I was a woman, but it was a very difficult situation there. And then women can't cut it at Scripps. They always drop out. And I've always wondered, if these things weren't being said, would this one be true? It's different now. It's different now. But it was a hard thing to do. But it wasn't all bad. We got married on the UCSD campus in 1982, right? I can never remember the dates. August 8th, okay. And it was a combination Orthodox Jewish hippie wedding, just like us. And then it was back up to Davis again. Rich started a master's program, and I went looking for a job. I want to introduce you to 2 people, very important people. One is Ed Berry and his wife Valerie. And they had a company called Atmospheric Research and Technology in Sacramento. Ed was one of the most innovative, clever people I've ever met, a really terrific scientist. He was a research scientist, a cloud physicist. And if you look, you can see the Berry stochastic method for cloud activation is still, I see it at talks sometimes. He invented these masks that one person could put up by themselves, but it was easier with 2. They were telescoping masks. They were extremely easy to move around, set up, and stable. We had an anemometer at the top, so they were measuring wind. That, I think, pretty sure is Valerie. So I walked into the situation where Valerie was doing field work, so I couldn't, women did field work at this company. And they were measuring wind all across the Southern California deserts in different places. They were prospecting for wind because their clients were the wind energy companies of California. And he taught me a lot of things. One about wind flow, that you want to set up your turbines just past the crest of the hill to get the higher wind speeds. And he was developing technology and selling it as part of the company to support the consulting work. And it was this whole combination of consulting and technology and putting it together. And it was very clever. And I worked for him, and I did everything. I did the field work, I did the data analysis, I wrote the reports, I interacted with the clients, and I did the trade shows, sold stuff too. And it was a very, very productive, good thing, because all the things I heard about, from Scripps, that women can't do this, women can't do that, and I just did it, and it was really, really nice. And the thing about Ed is that in 1983, this is the unemployment rate from 1975 to 2012 at the present, okay? And this is the Reagan recession, over 10% unemployment, 1982, 1983. In this recession, Ed started a company. He left academia. He was a researcher at Desert Research Institute in Reno. He went to NSF. He was in Washington for 2 or 3 years. He was a program manager at Washington, and he left it to start this private company that created jobs for over 20 people at the high point of that company when nobody could find work. And I decided at that point there was no greater good than to start a company, to employ people, to treat your employees ethically, to produce an ethical product. All the stuff we do in academia, all the stuff we do in the government, it's all fine. But it's not really good. Ed was turning wind into jobs. And I don't know. I mean, it always struck with me as being really important. But I needed to finish the PhD because I really needed it. If I was to go into consulting, I'd need that PhD by my name to be viable. And I went, we were living in Davis, so I started the PhD program in Davis. 6 years and 2 babies later, I left a draft of my dissertation on Brian Weir's desk as my advisor, And Rich and the boys and I drove to Baltimore. Okay, so this is how I arrived in 1991 at Goddard. And what did I do? I've talked to people before about my interaction, the job interviews, so I didn't want to do that again. I'm going to talk about my first project at Goddard. It involved measuring BRDF from Hasselblad cameras. This is Yuri Meckler. This is Yoram's advisor from Tel Aviv University. He was here for the summer. That's me. You can't see him in back, but that's Brent Holben. That's Eric Vermote. We went down to Wallops. We had these Hasselblad cameras at the back of the plane. We flew, we took pictures, and it was a lot of, it was really fun. This is Yoram and I. Bill Lazenby was the photographer from Wallops. That's his camera. That's, we did the same thing in Israel the following summer on an airplane, taking pictures of the surface. We did some work from a cherry picker also, because the plane was expensive. And there we are in Israel. And I don't know, can you see anything? These are the images from, they're monochromatic from the Hasselblad cameras. If you look carefully, you can see the vegetative hotspot and the little dark shadow of the airplane on there. You can kind of see it here also. So you can see there's circles. This is sunglint from the irrigation. So I still have all these pictures. We went and we were using the negatives. We digitized the negatives, and we were going to do BRDF. We're going to look at the surface reflectance as a function of angle for different types of surfaces. This is all Yuri Meckler's idea. And about this time, Yoram's saying, I would like to hire a geographer type. If you know somebody, let me know. Well, every time Yoram did something, he had so many ideas. I usually shelved them. So he always had to ask for something 2 or 3 times before I actually delivered it. So by the 3rd time he asked me, I said, you know, there's my husband. And Yoram got so excited. He so liked the idea of hiring a married couple. I mean, I don't know how to explain this to you, but and so he hired Rich in 1992, and it's Rich's handwriting around these circles. So Rich was the one who was choosing targets and doing the image processing. And we ended up starting working together from 1992 on. So why were we so concerned with the surface? Because you have to characterize the surface in order to do this problem. Now the original hazy clean day, you get around it. But if you wanted to march through without having to have 2 days worth of data to do the job, you needed to characterize the surface somehow. Then Yoram had an idea about the time I arrived that if SFIR and VIS channels are correlated, if we can correlate the surface reflectance at 2 places in the spectrum, we could use one to infer the other, because for most aerosols, you can see the surface much more cleanly at the longer wavelength. So the first paper that we published together was correlating AVHR 3.75 reflectance with a visible reflectance. And the problem is 3.75 is not the best channel to work with, so we moved to 2.2 by 1995, and we have these very famous ratios that I didn't believe. And Andy Wald and I spent a good part of our time trying to prove Yoram wrong. We've measured all over. And you know, you get deviations from the 0.5 and the 0.2. But not, for first order, it was right. And there was nothing I can do. But I really did try to prove him wrong that time. And the reason you do this now is in the visible, you see the smoke. In the longer wavelength, you don't. You use the longer wavelength to characterize the surface, and then you can tell what the surface is in the visible and derive how much smoke is above it. But we also had to characterize the aerosol model. We're trying to get ready to do this MODIS retrieval. And the aerosol model is the particle properties that MODIS isn't going to retrieve, which is almost everything, including size and absorption properties and things. And this is back in Israel in 1992. This is Brent and I. This is the pre-Sem Photometer. we were doing an almacanter. In those days, you did an almacanter by hand. One person would move it around the angles and read off the numbers, and the other person would write down the numbers. We would bring the numbers back to Shauna. Shauna would put it into the computer, and we would get almacanters. So this is before there were C-mills. And there were very few aeronets when we started, just a cluster here in the mid-Atlantic states and a cluster in Brazil. And this is the kind of work that we did. This came from the C-mills. This is from the mid-Atlantic region. And what we were learning here is a size distribution, how much particles, particle volume at different radii of particle. So there was a mode here around 0.1 to 0.2. There was a sea salt mode around 1. There was a coarse mode out here. And if you get really clean, you can see Pinatubo right there. And what we found, as you increase the aerosol optical thickness in this region, there was a shift in size of particle. And that was one of the first important things that I came up with here at Goddard. And in the Brazilian data, it wasn't really that same shift. So there were different kinds of particles, different substances. And we were using these Sem Photometry retrievals and not in situ measurements, because the in situ measurements are not ambient and they're not for the total aerosol, total atmospheric column. This is a paper that I published with Santiago Gasso in 1997. And these are the in situ data. This is what was measured, the dashed line, dry. And then if you hydrate it up to what the ambient conditions would be, it would be here. And that's a huge change. Now, I'm not saying it's wrong, but it's not truth either. It's another type of data. And all that data required collection in the field, which Rich and I did together and as a family. This is 1996 in Wallops. This is actually Sean Gao, Rung Rung and Bokai's son. These were homeschool friends from Baltimore, my sons. This is us in Mexico in 1998. So people ask you, how do you have children? Is it a bad career move for women to have children? Yeah. No, you just bring them with you. We just went everywhere together. And that's 1995, after we came back from Brazil. More people from the group. This picture is really important too. In this time period, there were about 60, 65 people in the climate radiation branch, 6 women in technical field, 3 worked for Yoram. Yoram, what's with all these women? Lorraine, I can usually get women cheaper, and they work for less. One of the many times I feel like hitting him. But it was so cute, you couldn't do it. So all through the 90s, there was a lot of excitement. We were learning new things all the time. Always someplace new to go, something new, always fun. And I mean, a girl couldn't have more fun. And then Terra launched, and it only got better. We had a global view of the aerosol system that we had never seen before. And this is a much later picture, because we have deep blue in here now also, but we could see the whole aerosol system and the size parameter over the ocean. No one had seen anything like that. It was just amazing. We could calculate the intercontinental transport. We could quantify the amount of aerosol that went from one coast to the other. This is something that Yoram led initially in 2005, something he had thought about when he was writing the proposal. And Hong Bin Yu has done much work in this field since then. There was a flurry of validation, of refinements, of documentation. This is from my 2005 paper. We were plotting MODIS aerosol against Aeronet aerosol over land and ocean to see how we were doing. How did we compare with the Sem photometers? And because these are global consolidations, a lot of bad stuff can hide in a global scatter plot. We also had to go into the field a lot and do some up-close ones. The boys are getting bigger, and Rob showed up.
Yeah.
That's right.
Here's another picture from Puerto Rico. And in Puerto Rico, we could look at dust up close, and we could do particular scatter plots right there. We could look at some of the climate effects of the aerosol. This is a paper that Yoram and I did together, where we took the over ocean, the MODIS product over ocean, and we calculated seasonal and regional aerosol optical depths for all these different regions, winter, spring, summer, fall, northern, winter. And then from that, we calculated the direct aerosol radiative effect from those particles, not the forcing from the anthropogenic. So it was, that was really cool. We were using the data to learn about aerosol cloud system in ways that were completely new. This is work by Ilan Koren and the rest of us. And if you plot aerosol optical depth as a function of cloud top pressure, as the more optical depth you get, the higher the clouds in the Atlantic. If you looked at cloud fraction at a particular level, the more aerosol, the more cloud fraction. Well, no one had seen this. Okay, and even though, you know, a lot of it may have been hand-waving, this came right out of the data. We were testing new technology. In the 2000s, things were changing. We had new people, new ideas. This is Vanderlei Martins. And we were up at Mount Evans with his new toy, the cloud scanner, testing the new technology. About this time, Yoram gave me the MODIS algorithm, moved on to other things. I'm not a data producer anymore, I'm a data user. Lorraine, you cannot sleep at night. But we went up to Mount Evans. We were still having a good time. That's Matis and Rich now at Mount Evans. That's back at the cabin. We had Ilan with us. And that was the science team. People don't recognize Rich without his beard. That's okay. His mother doesn't recognize him without a beard either. And that's me on the very tip of Mount Evans, working the data. Notice that women aren't good at experimental work. But I would say we couldn't have more fun. It was just really terrific. And we knew how to have fun. I mean, we were always together, always doing things. We did the Air Center started, and we gave out the golden simmies, like Oscars. And there's Yoram winning his golden simi. And Yoram knew how to have fun best of all. And then he died. And everything changed. Now, the groups stayed closely intertwined. It wasn't like we all disintegrated. By the way, that's Matis now. We continued to produce an outstanding product in exciting science. Nothing went away, you know, we were still doing it. This is our climatology from 2008, something Rich and I did together, using the MODIS data, looking at all the statistics. Ilan produces some of the most impressive cloud aerosol interaction work. This is his 2008 science paper. As optical thickness increases in the Amazon, cloud fraction first increases, then it decreases. We have a microphysical response and a radiative response. This is just unbelievable, this kind of exciting things that we were finding. This is his latest paper I was involved in. It's really messy, but it's polluted minus clean rain rates from trim of deep convective clouds. Now, red means there's more rain with more aerosol. The whole world is red. Deep convective clouds are associated with more aerosol. And we got together. You know, Ilan was in Israel. This is him winning the Young Scientist Award in 2008 IRS. And when we all got together, sometimes that old sparkle still come back, and it would be really fun. I could have stayed at NASA for the last 20 years of my career, but it wasn't as much fun without Yoram. And there were burdens connected to government service that had become very heavy. And Rob had ambitions and was ready to lead. And there were things I hadn't tried yet that could not be done while a government employee. And it was like all of these things. If it had just been that it wasn't as much fun with Yoram, I would have stayed. But then things got heavy. And if I had no one to give the group to, if Rob hadn't been ready, I would have stayed. Okay? But it was all 4 of these things coming together. And it was just time to go. And I want to go back to this chart. Because we had another recession, you know. And I'm thinking about Ed, and I'm thinking about ART, and I'm thinking about what's really good. What have I done that's really good? And I had a lot of fun. And I didn't do anybody any harm. But I didn't do anything really good. And I have all this education and talent and privilege, and I need to do something. And let me introduce you to Air Photon. Now you have to understand, I am a university employee with JSET, and I 100% salaries paid by the university through grants. And the university approves and encourages their faculty to start companies. Because the university's mission in the state of Maryland is to educate, to do research, and to do entrepreneurship. So I didn't know that. So we can do this. And Air Photon is our company. There are the 3 officers. We started last year. Randerlei is the technical officer. Rich does all the operational work, and I just kind of go along for the ride. We build automated aerosol filter sampling stations. These are 8 slots and a filter, a cartridge that holds 8 filters. You can start it and come back in a week. You can automatically change filters 1 per day. You can do all kinds of different kinds of duty cycles. This is the control box that controls this. We have 3 wavelength integrating nephelometers that do the forward and backward scattering independently. Here are instruments on the roof at Dalhousie University being tested. And here's the nephelometers back here, and the inlets and the control boxes. And we employ 4 people. This is one of our engineers. Pay taxes regularly to Maryland and the feds. And I feel like I'm really doing something, you know? That, not that John couldn't get a job because he's really good, but that we have created jobs and we are paying taxes. And I'm not just taking tax money, I'm paying back into it. And we're not taking wind and turning it into jobs, we're taking Canadian taxpayer money and turning it into jobs. I don't know, but we'll get there somehow. And so that's what I've been doing. And to have this opportunity to start a company and to give back this way couldn't be done as a civil servant. There's just too many conflicts of interest involved. So that's one of the really positive things about working for the university. You have a little bit more freedom to explore these different things. And I basically coming to the end here, and I just want to say that the reason I came to NASA was Yoram, and the reason I left was because of Yoram when he was gone. Okay, thank you very much.
I will take a few comments, questions, please. Yeah. All right.
So how does the cloud interfere with the remote sensing of aerosols?
What?
How do you separate the effects, cloud and aerosol?
That's hard. It's hard to get rid of the clouds. It's hard to separate clouds and aerosols. It's hard to separate clouds and aerosols with your eyes. It's hard to separate clouds and aerosols by in situ measurements. It's just a hard thing to do. We have different methods based on spatial variability, based on spectral signals, that on temperature sometimes, that you try.
The volcano, you can see the cloud is kind of bright white.
Sometimes, you go outside, a lot of clouds are not white. You can see all those dark clouds all the time, even not thunderstorms, but you can see a lot of dark clouds. A lot of aerosols are very bright. It's hard. And it's something that every time you go to use a new satellite instrument, you have to revisit this whole concept of cloud masking, how to make that separation. And you never do it 100%. You always have some contamination one way or the other.
Okay.
With the company, are you analyzing the data too?
Oh, not yet, but I assume we will be. Right now, our customers want to do it themselves, but I know that there are customers asking us questions about if we would do it for them. Yeah. With Ed and ART in California, he started from consulting, and he used the technology to support the consulting. Okay, so he started with the consulting first. We were in a position where we had to start with the technology because we had a customer in Canada who wanted it now. And so it's not the easiest way to do this because every time you build something, you have to buy all the parts. And they're a lot of money. So it's would have been nicer to build up some money first with the consulting and then move into the technology, but we're doing it backwards. We're taking investments. So.
Other questions? Yes.
Does Air Photon employ any women at this time?
No. Not at this time. But you have a women officer.
Yes.
Your boss.
Yes.
Yes.
All right.
You have to do it both ways. At home she is boss, at
One thing that perplexes me about state employees, as I'm married to a Maryland professor, and federal employees is it seems like state employees have kind of a full range of activities that you can do that federal employees can't, and yet you're still a government employee.
We went, before we started this thing, Jeannie, we went to all the different layers of UMBC. They have a name for it. It's not quite legal, but it's just the compliance officer. We went to the compliance officer, and then we went to the legal, and then we went to the intellectual property people. And we went to all these people and said, don't you have a problem? Isn't this inherently a conflict of interest? And the answer was, it's a conflict of interest, but it's a manageable conflict of interest. So I don't know.
You're really still a government employee.
We're still government employees, but the state of Maryland is so desperate to have us starting companies and employing their students and their graduate students and paying their payroll taxes that they just don't care. They want to turn that research from the university into something that's going to make money in Maryland. I don't know, Jamie.
Hey, last question. Yeah. You had a question.
The question I had is, any dealings later on with your friends from Scripps?
I mean, it wasn't everybody. I mean, I have very good friends. My classmates were good friends. The class just under me, we were friends. The professors who said that, no, I haven't actually seen any of them since then. Richard Somerville was not like that. Richard Somerville, who was my advisor, was very supportive. He was not on the qualifying exams that I passed. So my advisor was not there. So I don't want anything negative about Richard, but he was very good to me.
Okay, guys, as you can see, NASA is good at producing future CEOs. So let's